In this example problem, we'll give some interpretation to an example with some actual numbers in it, relevant to the definition that we just gave in the last video. So for this one, a population of fruit flies, so fruit flies, we'll use F to describe fruit flies, is modeled by f of t is equal to 1000 e to the 0.01 t power, where t is measured in hours. So as you can see, this does follow what the law of natural growth does indicate. Additionally, we can see right up top that our k value right here, that our k value is positive, which means that we are dealing with a growth model. So first and foremost, let's do part A. How many fruit flies are there initially? How many fruit flies are there initially? Now, with that in mind, the initial number of fruit flies is referring to the numerical coefficient of the whole thing, what we would refer to as f naught in this case. So f naught is referring to 1000. However, there is another interpretation that you can give to this. When we say the initial amount of something, or how many are there initially, we are assuming that we're starting at time equals 0 and that time progresses from there. So t equals 0 could represent, now, and then we move on from there. So we could say f of 0 is equal to 1000 times e raised to the 0.01 times 0. However, when we multiply by 0, the entire exponent becomes 0. E to the 0 power is the same as anything to the 0 power and simply becomes 1. Excuse me. So the interpretation that we can give to this, initially there are 1000 fruit flies. Initially there are 1000 fruit flies. Good. Next up, we'll say state and interpret k. Now, we already pointed out up top that our k value is greater than 0, so it is a growth model. But now we can give some significance to the fact that it's equal to 0.01. So k is equal to 0.01 can be interpreted in the following fashion. The fruit flies are growing, or I guess I should say the number of fruit flies is growing by a rate of approximately 1% per hour. 1% per hour. Now that's because we would interpret the 0.01 by moving the decimal place 2 to the right and taking that number as a percentage. So with an initial number of 1000, we are probably going to expect to see a growth of about 1% of 1000, which would be 10 fruit flies during that first hour. Now let's see if we can legitimize that. How many fruit flies will there be after 6 hours? Now, based on what we just said in part B, one of the things that we could anticipate here is the fact that, it's growing at 1% per hour. Initially, there are 1000, and 1% of 1000 is 10. So we could say that this is probably going to grow by about 10 fruit flies per hour. However, when we plug it into the model by saying, let's do f of 6, so 1000 multiplied by e raised to the 0.01 times 6 power. This is a point where we can allow the calculator to take over, and we'll take a look at the approximation of what we wind up with. So in our calculator, we'll type in 1000 times e raised to the power of, that's second ln to get e to the power of, and we'll use parentheses up here just to make sure, 0.01 times 6. So my intuition tells me that this should probably be about 1060, what we actually find out is that the answer is slightly bigger than 1060. If we round to the nearest unit here, and because these are living beings, we would round to the nearest 1, I would round this up to 1062. Now, the reason that it's slightly higher than the anticipated 1060 is due to the fact that as soon as the population starts growing, 1% of that population is now going to be slightly bigger than 10 fruit flies. Now, it's not a lot bigger. In fact, it would be represented as a decimal for the first little while. But this is what we mean when we say an exponential growth function, is that this thing is growing not at a constant rate. So it's not just a flat 10 fruit flies per hour, but 1% of the population as that population is growing. Now, we can also use a model like this to make predictions about the future. How long until the population hits 1500? Now, when I say how long, it's implied that what we're trying to find is how much time will that take. So how long until the population hits 1500 is asking us to set the population equal to 1500, and then to use algebra to solve for t. So that's what we'll do. In order for us to do so, we are going to have to make use of those fancy new logarithms that we talked about recently. So we set the left-hand side equal to 1500, and from here we'll do algebra. The first algebraic step for us is going to be to isolate the exponential. We isolate the exponential by saying, let's go ahead and divide both sides of the equation by 1000. Now, normally you wouldn't have to, but you can simplify this fraction. We'll take it down to a decimal and we'll call it 1.5. The reason I'm okay with decimals here is because we're eventually going to be rounding in the calculator. This is a real-world problem, so we'll give a real-world answer. The next thing that we're going to do is we are going to take the natural log of both sides, or the natural logarithm of both sides. The reason is a natural logarithm is the inverse function to the natural exponential. What will happen is that on the right-hand side, the natural logarithm and the natural exponential will cancel each other out. We'll be left with 0.01t on the right-hand side and the natural log of 1.5 on the left side. For a final act of solving, we'll divide both sides by 0.01, which will allow us to get the right-hand side as simply t equals. So this will be, as an exact answer, t equals the natural log of 1.5 divided by 0.01. We can turn to the calculator for an approximate answer. So natural log of 1.5, close parentheses, divided by 0.01. Looks like if we were to round to the second decimal place, this will take approximately 40.5, well, it's a 4 with a 6 after it, so we'll round that 4 up to a 5. We'll call that 40.55, and then the units of time that were given in the problem, hours. Now, this part D that we just went through is going to be very closely related to the subject of the next video, which we'll go ahead and introduce right about now.